got a couple scary looking integration questions here where we're going to apply U-substitution. I do advise you to attempt these and then compare them with my final solution. So on to this first one. The only real struggle with U integration is to decide on what to set as your U. So in this particular case, we've got a couple real examples. Cos squared x could be U, tan x could be U, or 1 plus tan x could be U. Let's consider setting cos squared x as U. The derivative of that, du, would be on the lines of 2 negative sine of x. I don't see how we'll be able to cancel out the 1 plus tan x through that. If we attempt to make 1 plus tan x as u, our derivative would be secant squared x. Secant squared x, that has similarities with cos squared x. I do see possibly a cancellation there. So let's go about that. Let u equal to 1 plus tan of x, which further means that du would equal to the derivative of 1 is 0, tan of x is secant squared x dx. This could also be written as dx is equal to du over secant squared x. If we plug this information back into our equation now, our integration would look like the integral of du over secant squared x, all of that divided by cos squared x, which we haven't changed at all, multiplied by the square root of u. This can also be written as the integration of cos squared du divided by cos squared x of square root of u. Fantastic, I've gotten rid of the x's, and now I'm left with a very simple integral that only involves one variable, which really is the only purpose and function of u substitution. This can then be written as u to the negative a half. We use a simple integration law where we add 1 to the numerator and put it in the denominator as well. So this would become u to the 1 over 2, negative 1 over 2 plus 1 is 1 over 2, divided by 1 over 2 plus c. Now we've only got to plug back our u substitution into our u. So we have our final answer in terms of x. So we will have 2u to the 1/2 plus c, which is 2 square root 1 plus tan x plus c as our final integral. That's the first question. On to the second one, which is slightly trickier, especially with the bounds. So we're going to have to find a final answer. Now right here, we've got limited options. I see 1 plus x to the 4 and x. If we try setting the denominator as u, our derivative would be 4x cubed. I don't really see any relation with that and the x there. I could try to set the numerator as u, but then again, I'll be stuck. Recall, the derivative of tan inverse of x looks similar to this function right here. It's x over 1 plus x squared. We've got an extra x squared in the denominator. So let's attempt to set u as this surplus x squared that we have in the denominator. That would mean our u is equal to x squared. Now, at this point, I don't quite know if I'm doing the right thing, but there's no real harm in trying. It's the only way to learn. Du would be 2x dx, and dx will be du over 2x. I'm going to plug all that into my equation now. Saving space, I'll go right here. I have x multiplied by du over 2x, all of that divided by 1 plus u squared. Now this right here, I see if I move the 2x into the denominator, I could cancel out the x's and I'll be left with only one variable in the integral. So this would then become, let me just show you the step right here, x du divided by 2x multiplied by 1 plus u squared. X's cancel, and I'm left with a friendly looking integral now. Of course the bounds are still there, I haven't really written them because I'm trying to find the antiderivative first. Now I'm going to pull 1 over 2 out. Another simple integration law you should know before doing u integrals. We're left with du times 1 plus u squared. Now that is definitely the derivative of the tan inverse. So the antiderivative of that is equal to 1 over 2 tan inverse of u. And we have our bounds. Now back to our bounds. These bounds are in terms of x. What have we applied to x for u? Every u has an x squared, and these bounds are just for an x. So we also need to square the individual bounds. The upper bound would become pi over 4, and the lower bound 0 squared remains as is. Now we're going to apply the fundamental theorem of calculus, where we plug in the upper limit and subtract it from the lower limit. Tan inverse of 0. Tan inverse of 0 is equal to 0. Recall the graph looks kind of like this. At 0 it's equal to 0. So our final answer would be tan inverse of pi over 4. I don't quite know the exact value for that. I don't think you'd be expected to know that. And that is our final integral with the bounds.